Hi, this is Matthew Crump. I'll be demonstrating my final project, which is a logic analyzer open source project that's supposed to be able to run on any FPGA and be easily customizable. And right here I have two FPGAs. This one runs at 100 megahertz and this one runs at 12 megahertz. This one has been configured to have a memory depth of about 8,000 and has 8 channels on the logic analyzer. And then this one is configured with a memory of 4,000 and has 16 inputs on the design. This one in particular is reading this SPI sensor, and then this one is just reading the input switches. Essentially, logic analyzers are for debugging digital designs, as they allow you to capture all the electrical signals that are going through the chip, either internally or externally from a sensor. And so I'll show a demo on each of these. I also wrote a GUI in Python that shows the data once it's been saved to the computer. And what we have here is two instances of the GUI open. The one on the left is configured for the smaller FPGA with the SPI sensor, and the one on the right is for the one with the 16 DIP switches. And the GUI has these configuration files that just tells it what the frequency is, what the memory depth is, and how many channels are on it, and all the other parts are optional. And that will configure the GUI to have a different number of traces, as you can see here. And so what we can do is we can set up which channel we want to watch on, and we're going to just pick the second channel, and we want it to be a rising edge. So when it goes from low to high, we want the memory depth to be 10, and the sample rate we want to be every 5 microseconds, which gives us a minimum record time of 20 milliseconds and a maximum record time of 5.5 minutes. So if we click that, and then we click capture, and then we can click start, it's now waiting for the second switch to be flipped, which is this one. So if I just sit here and toggle this one, nothing happens. I toggle the other ones. But if I toggle that second one, you can see that LED lit up. And now you can see this LED lit up, and it sent the data over. And now it just barely plotted that data. And this red little marker right here shows you where the trigger point happened. And we can just zoom in here, and we can zoom out. Yeah, and then what we can do is we can get time measurements by clicking here and then clicking on a second point. And down at the bottom it tells us right here what's the interval there. If we click somewhere else, we get the other time result from there. And this one over here was the SPI one, the other FPGA that was sitting there. I had it set to channel 1, falling edge, at 10% before the trigger point, and then at sample intervals of 83.33 nanoseconds. And we can get some timing information here. The chip select line is low for 10.6 microseconds. The clock period is 639 nanoseconds. And this way we can verify that everything's working and make sure the timing's right. The other thing that we can do is we can save this current one if we wanted to, but I'll just open a previous one. I'm just going to pick this one, and I can click open and just give it a second to load. And this is a saved file from a previous capture, It properly marks the correct trigger channel. It gives you the correct sample time based on what you recorded it at, and that was 4 seconds there. And up here at the top, it shows where the source is, if it came from the logic analyzer, if it came from a file. And then we also can select which serial port we were connected to. We could save the configuration file. There's exit button. We also can reset the view. And then it shows, you can see the SPI bus talking every, let's see, every 54 milliseconds it talks back and forth, and we can just keep zooming in. It's kind of hard to zoom clear in on it, but yeah. And then the other last little part to show is in the source files, as soon as I open it. So in the top file, I've tried to make it really easy to change the number of inputs. So the only thing you have to do to change that is just change that number, and this number will change how many rows in the memory in the RAM that it uses. And that's essentially the project. I guess the last little thing is once you start a capture or whatever you're doing, it gives you a little status saying it's waiting, no trigger has happened. When a trigger point happens, it updates and lets you know. And then once it does read it, it's letting you know that it's reading, and then it's ready again. And then there's the data updated. And that also tells you how many data points came before and after the trigger point. And that's my project.